welcome everyone. Welcome to the Northwest Database Society Symposium. And we are super happy to have with us today Rebecca Taft. Rebecca is I forgot your title, at Cockroach Lab, but working on their database engine, which is super exciting. Before that, she was at MIT, where she graduated working with Mike Stonebreaker. So very, exciting background here. And we're just so happy to have you here and have the opportunity to learn more about the query optimizer, right, of CockroachDB.
Awesome, great. Thanks for the introduction, and thanks so much for having me. I think I cannot, there we go. Let's see, just gotta find, here we go. Find the right screen to share. Present. All right, can you all see that? Awesome.
Yes.
Cool, well, thanks again for coming. I am just a software engineer at Cockroach Lab, so not surprising you couldn't remember my title. It's pretty boring. I'm on the query optimizer team, and that's what I'll be telling you about today. And for those of you not familiar with CockroachDB, it's a database that was built with the mission to make data easy. So as the name Cockroach implies, it is resilient to disasters, even intended to survive the failure of a whole data center. But it's also scalable, and it can scale out as an application grows. Its geo-distributed capabilities allow the data to reside physically close to the users that will actually be using it. It supports full SQL with serializable transactions, so that of course simplifies OLTP application development, and it's open source. Just to give you guys an idea about how our customers are actually using CockroachDB, this is a real deployment from one of our customers that has markets in Europe, Australia, and the US. And by having data centers actually physically located in each of those locations, they can provide low latency access to their customers, low latency access for their customers to their data, and also comply with local regulations like GDPR, which requires that the private data for EU citizens has to physically reside in the EU. It simplifies the life of application developers because they don't have to worry about manual sharding or anything like that. The database takes care of all of that and provides transactional guarantees. And you can see it's also very resilient to disasters because even if an entire data center fails, the database will be able to continue serving requests. So in order to support workloads like this, CockroachDB has a shared nothing architecture, and it consists of a distributed SQL layer on top of a distributed key value store. Now in this talk, I'm really not going to touch on the key value store at all, but there's a lot of really interesting stuff there. If you're curious, I encourage you to check out our Sigma paper, which we published last summer. And I can also try to answer some questions at the end if there's any specific questions you have about our transaction model or any of that. So this is an agenda for the rest of the talk. That was a super whirlwind brief overview of CockroachDB. And for the rest of the talk, I'll be focusing on query optimization. So before I get started, any questions about the database overall? Feel free to just unmute yourself and shout out. I probably won't be checking the chat super regularly. All right.
So maybe actually just one quick question. I forget, does CockroachDB provide strong consistency for transactions?
Yeah, it's serializable isolation. So it's not as strong as Spanner, which is linearizable, but it's serializable and actually slightly stronger than that because it provides single key linearizability. So if you're just looking at a single key, there's no stale reads basically.
Okay, thank you.
Yeah, great question. Okay, so query optimization and CockroachDB. So Cockroach supports SQL, as I mentioned. And so, of course, we need something like a query optimizer to convert that declarative SQL statement to an execution plan that the database knows how to execute. So you might say, well, and actually specifically, we support the Postgres dialect of SQL. So you might be wondering, there are lots of existing open source optimizers out there. Why not just use one of the existing ones? For example, since we support the Postgres dialect, why not use the Postgres optimizer? Well, there's a few reasons for that. One is that the CockroachDB codebase is written in Go, and Postgres and other optimizers are written in different languages. Postgres is written in C, and there is some amount of overhead required to translate between Go and C. We want the planner to be as fast as possible, so that's one reason. Actually, we were previously using RocksDB as our storage engine. I told you I'm not really going to go into the bottom layers of the database, but just to mention that RocksDB is written in C++, and we just recently replaced it with our own homegrown LSM tree called Pebble, which was written in Go. And one of the reasons for that was because of this C++ Go barrier and the performance overhead that it incurred. Another reason that we decided not to use an existing open source optimizer was that the execution plans often look very different. So Postgres is a single node database, whereas CockroachDB, as I showed you, is a distributed database, and a plan that might perform very well on a single machine might perform terribly when it's extended to a distributed environment like CockroachDB. And finally, the optimizer, as I'm sure you're all aware, is critical to the performance of a database. And of course, as a database company, we wanted to have control over this important component. The performance difference between the best plan and the worst plan can be orders of magnitude. All right. So we decided to build an optimizer, but CockroachDB's first optimizer was actually not really an optimizer. It was a heuristic planner, and it used heuristics or rules to choose the execution plan. So these rules would look something like, if an index is available on the attribute of filter condition, always use it. Pretty simple, makes sense. But the problem is it's very difficult to write rules like this that are always going to be a good idea in every scenario. So as CockroachDB was used in more and more different types of workloads, these rules got more and more complicated. So this simple rule might become something like, always use the index, except when the table is very small, or we expect to scan more than 75% of the rows, or the index is located on a remote machine. So not ideal, kind of brittle, as you can see. And it sort of works okay for OLTP workloads, but the problem is that our customers will run everything. When trying to decide what database to use, they might compare us to our competitors by running TPCH, for example, classic analytics benchmark. But even in production, a lot of our customers will run kind of OLAP type queries, like maybe at the end of the day, they'll run kind of a end of day roll up type query, and they don't want to actually outsource that to a data warehouse. They would just rather run it on their transactional database. So, we had to basically not perform terribly when these types of queries were run by our customers. So by the time I joined Cockroach Labs a little over 3 years ago, the decision had been made that the heuristic planner had outlived its usefulness, and it was time to build a real cost-based optimizer. So you're probably familiar with the fact that a cost-based optimizer, basically, instead of applying these rigid rules, it considers multiple different alternative plans. And it assigns a cost to each of those alternatives, which is kind of like an estimate of how long the query is going to take to run, or how many resources are going to be required to run the query. It's a unitless number, but a way to kind of compare different plans. Then we choose the lowest cost option, and that's what gets sent to the execution engine to execute the query. And for those of you familiar, we decided to build a Cascades-style query optimizer with unified search. This doesn't mean anything to you. Don't worry about it. I'm going to explain what all this means. So how do we generate these alternative plans? Well, we start with kind of a default plan that you can almost mechanically construct from the SQL query. And then we perform a series of transformations to transform the query into logically equivalent alternatives. And we store all these alternatives in a compact data structure called a memo, which those of you familiar with optimization probably know what a memo is. If you don't, I will go into it in detail in a few slides. And then, as I mentioned, we assign a cost to all these alternatives. So there's a few different factors that affect the cost. Things like the hardware configuration, like how much CPU, RAM is available. What's the data distribution like? Do we have a geo-distributed cluster where data is spread between Europe, the US, and Australia, or is it all located in a single region? What are the type of operators in the plan? So it's going to be more expensive, for example, to perform a scan, which might require disk I/O, than it is to perform a filter, which is just a CPU operation. And then the number of rows processed by each operator affects the cost as well. So it's going to be much more expensive to scan 1 million rows than 1,000 rows. Any questions before I move on?
Is the memo also known as and or DAGs in the literature?
What was that? Sorry.
So I've seen the term and or DAG in the literature. So is that another name for the memo?
And or DAG. I have not heard the memo referred to that way, but it's definitely possible.
Okay, yeah. So if you,
I'll get to the memo in a second, and then it might make a little bit more sense. I don't think and or DAG would make sense to label the memo, but
okay, thanks.
But yeah, let me know when we get there. Okay, so generating alternative plans. So in this section, I will go through each of these phases to explain how we generate these different alternatives. And in this section, I'll use this sample query you see here. It's a very simple join query that's using these two tables, A, B, and C, D. You can see that there is a secondary index on table A, B. I'm performing a join on B equals C where B is greater than 1. Okay, so starting with parsing, I'm not going to really go into too much detail here. Parsing is pretty much the same across most database systems. We're basically taking that SQL string and converting it into an abstract syntax tree. But this is kind of cool because I'm just showing you here what the actual Golang structs look like after this abstract syntax tree is created. So, and our grammar looks very similar to the Postgres grammar. Our YAC file is mostly copied from Postgres. So, okay, so we take this abstract syntax tree, and in the next phase, the Optbuilder, we basically are constructing this mechanical execution plan that I was talking about before, kind of just the default, simplest, non-optimized query plan for the SQL query. And the way this works is we call a bunch of nested functions like you see here, construct select, construct inner join, and that is basically how we build up the query execution plan. Another thing that happens in the Optbuilder is semantic analysis, and this basically makes sure the query makes logical sense. So the parser has already checked that the query is syntactically correct, and in the Optbuilder phase, we check that it's semantically correct. This is kind of analogous to with an English sentence. Something might be grammatically correct, but it might not make any logical sense. So for example, these two sentences here are grammatically correct, but who knows what they actually mean logically. And in the context of our SQL query, the semantic analysis phase will ask questions like, are A, B, and C, D real tables in the database that the user has permissions to access? Do these columns B and C exist? And are they unique, or is there some ambiguity? And is it even valid to compare them for equality like we're doing here? And what columns are selected by that star? Okay, so normalization. Now I've shown these two phases, Optbuild and normalize, as two separate phases, but in fact they're happening at the same time, and I'll show you how that works. So in the Optbuilder phase, we're calling these nested functions, and the Optbuilder thinks it's constructing this default plan you see here. So this query plan in the middle is equivalent to calling those function calls on the left. But in fact, this plan that you see here never actually gets materialized, because what happens is that in the process of making these function calls, various normalization rules fire, and these transformation rules happen before the plan even gets materialized. So even though the Optbuilder thinks it's constructing this plan, in fact, it constructs this plan that you see here on the right. And so a couple of things have happened. Basically, we have used the fact that B equals C to infer that if B is greater than 1, then C is also greater than 1. So we've kind of generated this additional filter. And then we've taken those filters and we've pushed them down below the join onto the relevant side of the join. So maybe this looks a little bit like magic right now, but I'll explain how this works.
A quick question here. So yeah. you say you use the word normalize. Normalize makes me think that for every query there is a unique normal form that gets that query. So what happens if you have multiple joins? Does a normalization also choose a normalized order of the joins?
That's a great question. Yeah, so it does choose a normalized order, and that just matches the order that's provided in the query. So, if you say A join B, that is going to correspond to a normalized join ordering. We don't perform any join ordering during the normalization phase. That happens in exploration, which I'll talk about in a second.
Okay.
Cool, thanks. All right, so these normalization rules are rules that are basically always a good idea. So we, always want to apply them, and we know that it's always going to be superior to what was there before, so we don't even bother to keep around the old plan. As I mentioned, that default plan doesn't actually get materialized. It's only the normalized plan that actually gets stored in the memo. So normalization rules are things like elimination of unnecessary operations. So like not X is equivalent to X, and of course, better to not have to execute both of those nots during execution time. We also canonicalize expressions during the normalization phase. So it's not that X equals 5 is more efficient than 5 equals X, but by performing this canonicalization, it allows us to more easily apply other rules. So we don't, the other normalization rules don't have to check both ways. When 5 equals X and X equals 5, they can assume the variable is always going to be on the left, so they only have to check one of these options. Constant folding is important. Length ABC is equal to 3, and of course, it's more efficient to not have to execute length of ABC for every row during execution, but also it allows other normalization rules to fire, like constraining indexes and things like that. And then these last two, predicate pushdown and decorrelation of subqueries, are not technically always a good idea. You can find examples where it might actually be more efficient not to push down the predicates, but in practice, those are so rare that it's better to just treat them like a normalization rule and always perform that predicate pushdown. So as you're not familiar, predicate pushdown is basically pushing filters as far down the query tree as possible so that higher up operators don't have to execute on as many rows. And then decorrelation of subqueries is if you have a subquery that refers to an outer query, we actually try to hoist that subquery up into a join or some other operation that's going to be more efficient to execute. So how do we actually represent these normalization rules? Well, we have a domain-specific language called Optgen, DSL. And Optgen looks something like this. It's basically a way to represent the normalization rules, normalization and exploration rules actually in kind of a declarative form that's very easy to understand and easy to write. So this is a super simple rule. This is that, not X is equal to X that I showed you on the previous slide. But I'm showing it here because it's representative of all the rules. They all have the same form. And it basically consists of, you have some comment at the top explaining what the rule does. Then there's a header. Eliminate not is the name of the rule. And then there's some tags. This normalized tag indicates that this is a normalization rule. Exploration rules have the explore tag. And then we have a couple of other different types of tags that aren't super important here. Next, we have this match pattern. So if you have two nested knots, then that would match according to this match pattern. The input is a variable that gets bound to whatever is inside the knot. So star means can be anything. And then the replace pattern after this arrow you see here just returns what gets replaced. So if we have this double knot, then we return the variable input. And this actually gets compiled into Go code. So it gets built in with the rest of the CockroachDB binary. And it looks like this. So in the process of constructing a not operator, we can execute any number of rules. So any rule that affects not will get co-generated and built into this function. So, in the process of constructing a not, if we see that there's a nested not inside, then we might call some callback functions, but eventually we will just return the input to the not. But if none of these rules match, so we get to the bottom of the function, you can see we have memoize not. That is basically putting that operator into the memo, which I'll talk about in a second, and then finally returning it. And you can see this construct not is one of these factory functions that the Optbuilder calls in the process of constructing a relational expression. So you can see that even though the op builder thinks it's constructing a not, in fact, it may return something completely different if any of these rules fire.
So I have a question, Rebecca.
Yeah.
One question is, so as you construct the tree and you fire these rules, could I write a rule that says, oh, actually, you know, when you look at the not, can you go up 2 levels in the tree and make some other modifications to the tree? Or can I only make a modification to the subtree and return some kind of node in that subtree?
Yeah, that's a great question. So it only operates on the subtree. So if you want to have something that affects a higher up operator, you have to basically create a rule at that higher up level. So, you know, we do that in some cases, like the rule might show multiple nestings. Like, you know, if you have, say, a select and one of the filters contains some expression that itself contains a not, then, you know, that might be the match pattern for a particular rule. Does that make sense?
Yeah, thank you.
Yeah, good question. Okay, here's another rule. This is called merge selects, and it basically takes 2 nested select operators, concatenates the filters, and combines them into a single select. And the reason I'm showing you this rule is because it shows another feature of Optgen, which is the ability to call arbitrary Go code. So, you know, there's all of these different keywords like select corresponding to select expression, not that I showed you on the previous slide. But if we want to do anything a little bit more custom, we actually have the ability to write arbitrary functions in Go and call them from Optgen. So the generated Go code looks like this, and you can see where I've pointed with the invoke custom function that we're calling this custom concat filters function, which is literally just concatenating these 2 slices or arrays together. So simple, but it shows you the power of Optgen that we can basically call any arbitrary Go code.
I have another question.
Yeah.
So you showed us, on the one hand, you showed us these very nice rules that you had like on the previous slide, which are very easy to read, like this one here. Very easy to read, very easy to verify. And I suppose you have a large collection of these rules. I want to ask you at some point how many rules you have.
Yeah.
On the other hand, you convert them into what you showed us on the next slide, which is very hard to read, very hard to reason about if you want to check the rules. We faced exactly this problem in one of the projects. We wrote a verifier for rules, but both Postgres and Microsoft SQL Server, they store their rules like you have on the next slide, like they are embedded in the code. So it's difficult to extract them and start to reason about the rules themselves. So I wanted to ask you, what solution did you adopt? Do you actually write the rules like this and they're automatically converted into Go? Or do you have to write them directly into Go?
Yeah, no, this is what we do. This Optgen syntax that I'm showing you here is how we represent our rules. And we have, I think I listed the number on a later slide, but I think it's something like around 250 normalization rules and maybe 40 exploration rules, or something along those lines.
Oh, this is great. So it means these rules are separate. They're kind of a knowledge base of all the rules that Cockroach applies. Yeah,
right. So we have a separate function suffix like .opt or something like that, where it stores all the Optgen rules, and not all of the rules are stored in a single file. They're kind of separated into logical files, like all the rules that affect select or all the rules that affect join, things like that. We try to kind of group them into logical groups. But yeah, no, it's a great question about testing. I mean, I think there is a lot of, because we have this ability to call custom Go functions like this concat filters function that I'm showing you here. There, of course, are, I don't even know how many lines of code, thousands or hundreds of thousands of lines of code of these custom functions that get called by the different rules. But by having this, what's the word? Kind of declarative syntax for describing the rules, it kind of just makes them a little bit easier to understand and process. And of course, we have lots of tests. We do have some nice testing infrastructure that allows us to say, call out these rules by name. Like, I expect in the process of optimizing this query that it's going to fire the merge selects rule. And then if we don't fire that rule, it'll cause the test to fail. you know, things like that. But, you know, you're right. There's really no good solution when you have a complex set of rules that you're trying to optimize with. There's always going to be weird interactions between the rules and yeah, lots of testing surface area.
Yeah, but it's very nice that you have isolated the rule knowledge base and using this syntax. I think that's an advantage over other systems.
Cool, thanks. Yeah, we really like it. I think it's turned out to be a great decision in the end. I mean, obviously writing the DSL up front was not trivial, but it's I think it's paid its dividends. Cool. All right. Any other questions about normalization before I move on? All right, so exploration, of course, is the other kind of rule. Exploration rules may or may not produce a better plan. So instead of replacing the previous version of the plan, we store all these different alternatives. And so the examples of exploration rules are join reordering, choosing the specific join algorithm, so hash join, merge join, lookup join. Lookup join is like an index nested loop join in other databases. And choosing and selecting the specific index is also an exploration rule. So, okay, so actually storing these different alternative plans brings me to explain the memo. The memo is a way to efficiently store a forest of plan trees. And it consists of all these different groups where each group represents one relational expression. So after normalization, there's just one expression per group, but as we perform exploration, we will add more expressions to each of these different groups. So you can see, you know, group 1 is the join and 2 is select and so on. We actually have groups for scalar expressions as well, but I'm not showing them here because it's, you know, not really that interesting and not important to understand the concept. Another important feature of the memo is that these groups can refer to each other. So you can see group 1, the inner join, is a join between groups 2 and 3. And that is very powerful because it allows us to represent many different plans just in this compact structure. So as we start adding expressions, that inner join between groups 2 and 3 is going to represent multiple different trees. So this will make more sense as I show you actual exploration and what this looks like. And just to remind you, this plan here on the right is the normalized plan of our example query. And this is what the memo looks like after normalization for this query. Okay, so as we start exploration, basically we're going to be, it's actually recursive, but you can think of it as kind of iterating from the bottom up and using our match and replace rules to identify exploration rules that match. So the first rule to match in this case is called GenerateConstrainedScans, and it basically allows us to generate an index scan on the secondary index on column B of table AB. So we add that to our group 4 since it's logically equivalent to scanning the primary index. Next rule to fire is GenerateConstrainedScans, and that basically is logically equivalent to the select b is greater than 1 on group 4, and basically allows us to push that predicate b is greater than 1 down into the scan into the secondary index on B. So we're basically scanning everything from b is equal to 2 higher. So it allows us to avoid scanning some data that we don't need. And then we can, again, match the same rule, GenerateConstrainedScans on group 3, where we're pushing the filter down into the primary index on CD. Next rule to match is ReorderJoins. So we had that join between 2 and 3. Now we're joining between 3 and 2. And an important thing to note in CockroachDB is that we don't really distinguish between logical and physical operators. The default inner join in CockroachDB is a hash join. So when we swap the order, that basically just changes which side of the join is used to construct the hash table and which side is used to look up into the hash table. Next rule to match is generate merge joins. So we can create a merge join when both sides of the join are sorted on the equality condition. And we do have expressions in groups 2 and 3 that are sorted on B and C. So we can construct a merge join. Lookup join is another rule that matches. As I mentioned, this is like index nested loops join other databases. So it's kind of like a hash join, except the hash table is actually the index from one of the sides of the join. So it's kind of like a hash join where the hash table is already built and we're looking up into the index. And there's even more expressions, but I think you get the idea by now. So as it turns out, the best plan in this memo is the merge join with the two constrained scans. And I'll show you how we determine what the best plan is in a second. But hopefully this kind of gives you a sense of the power of the memo, that we only have 5 groups and 11 expressions, but we're actually able to represent 20-something different plans just in this compact data structure. So this is kind of the merge join split out from the memo so you can see it more clearly. And that is what is going to get passed to the execution engine. Any questions before I move on?
Do you allow self loops? So or any kind of loops in the memo? That's
a good question. If there are loops, that's a bug, and we've definitely run into cases where that's happened before. So we try to avoid that happening, because that can cause stack overflow, basically, if there's any loops in the memo.
Interesting. Yeah, so I'll come back to this in the end. So we wrote something that looks almost exactly the same, that we can have loops.
Oh, okay. I'll be curious to, maybe you can tell me how you guys handle that issue. Cool. All right. Well, I'll keep going for now, just in the sake of time. So this last phase, dis-SQL planning, is currently not part of the optimizer. It happens after query optimization is done, and it's basically another heuristic application of rules where we convert that plan, which, as you saw, was really a plan designed for a single node, and we convert it into a distributed plan that will work across nodes in a distributed setting like CockroachDB. Now, we definitely want to move some of these decisions in the dis-SQL planning phase into the optimizer, and we're actively working on doing some of that right now. But currently, all of this happens after the optimizer. So, there's a lot of decisions like, well, we know that, the data in the primary index on table CD that has data range from 3 up exists on node 3, so we have to plan there. That kind of stuff the optimizer doesn't really need to know about. But decisions like, do we want to do a broadcast join or, a shuffle by hash, those kinds of decisions should really be made in the optimizer, and currently they're not. Okay, so any questions? Moving right along. All right, so how do we actually choose a plan now that we have all these different alternatives? Well, as I mentioned before, we have several different factors that affect the cost, hardware, data distribution, types of operators, and so on. And as I just showed you on the previous slide, we're not really taking data distribution into account as much as we should be, as much as we would like to be, but we're working on that. And if there's time, I'll show you how we do take it into account currently in some very specific cases. Hardware configuration, we're also not really taking into account. That's difficult, especially when you're working with a database that can run on any public cloud or in any setting, but ideally we would take that into account as well. And then between the type of operators and number of rows processed, both of those are included in our cost model. In practice, it's relatively easy to distinguish the cost of operators. We can just kind of run some benchmarks to determine the relative cost between operators for a given number of rows. But then the number of rows processed by each operator is very specific to the particular query and the particular data that we're running on. So that's what I'll focus on for the next few slides. So how do we actually find the number of rows processed? Well, we use statistics, of course. And the way we do that is we collect statistics in the background on every table in the database, kind of separate from query optimization. So for each table, we collect the row count. And for each column in the table, we collect the number of distinct values, the number of null values, and we also build a histogram. And the number of buckets depends on how frequently we expect the column to be used, but that's kind of a detail. And then we use those stats to estimate how the number of rows changes as data flows through execution plan. So let's look at our previous example just to kind of see how that works. So starting with group 5, say that we have this information just collected offline as I was explaining. We know that there are 4,000 rows in the table CD, and we have this histogram on column C that has a distribution looking something like I'm showing here. And similarly for table AB, we know there's 4,000 rows, and the histogram on column B looks something like this. So now we are going to propagate these stats up the tree. So from group 5, we can propagate those stats up to group 3 by basically selecting all the data for C is greater than 1. And based on that, we can estimate that there's going to be about 1,500 rows in group 3. And similarly for group 4, we can propagate that up to group 2 for all the data where B is greater than 1. And finally, for the join, we're essentially taking the intersection of these two histograms. It's a little more complicated than that, but you kind of get the idea about how we would calculate that there's approximately 500 rows at this top level.
So a quick question, Rebecca, what kind of histograms do you use? Like equi-depth histograms? Do you use something special for heavy hitters?
Yeah, it's just equi-depth histograms. Yep. We don't do anything special for heavy hitters. I mean, the equi-depth histogram, it's kind of special buckets where we track not just the number of items in the bucket, but also the number of items equal to the upper bound. So in that sense, I guess you could call it some way of tracking heavy hitters. So if the heavy hitter happens to be the upper bound of a histogram bucket, then we will count the number of items equal to that value, which, in practice, if there's a serious heavy hitter, then yes, we would be able to track the number of values for that, but we don't really optimize for that, if that makes sense.
Okay, so then one quick question. So why do you keep track specifically of the number of items that are equal to the upper bound?
Well, I think that's the idea is that, as we're constructing the histogram, we kind of basically, for most histograms, we store 200 buckets. And so, we try to we collect about 10,000 samples, and we try to split those 10,000 samples approximately evenly. But as we're creating histogram, once we get to the upper bound, we'll continue to include data items in that bucket that are equal to that upper bound. So in practice, if there is a very heavy hitter, it would probably end up being the upper bound. And it's just a way to kind of store a little bit more information in, in an efficient way.
Okay, thanks.
Yeah, sure. Okay, so now we have the number of rows in each of the groups, and then we can basically do what I was saying before for estimating the actual cost of each of these different expressions. We use the type of operator, so scan or select, and since we've already done some experiments to kind of understand the relative cost between them, we basically have kind of hard-coded values for the cost for each of these different operators depending on the number of rows. It's a little more complicated than that, but more or less, we say, okay, 4,000 rows, how expensive is it to scan 4,000 rows? That is the cost of this operator. And then we'll take into account how many columns are scanned, things like that. But more or less, that's how we come up with the cost. Does that make sense? Any questions about that?
Yeah. So Rebecca, today we are running a class on database systems, and a few people on this call are actually in that class. Today it happened that we just discussed this paper that we love so much. It's called "How Good Are Query Optimizers Really?"
Yeah.
It's a big paper, and they show that this problem that you have here on this slide, estimating the number of rows, is notoriously difficult, and that database systems do a very poor job of estimating correctly the number of rows. I wonder if you have more insights. So does Cockroach Lab do anything much better than it's in that paper, or do you expect to have kind of similar performance as the other systems?
Yeah, I would expect that we're not going to do much better on those types of benchmarks, on that, like the IMDb benchmark, for example, the join order benchmark. I think at one point we might have tried to run that benchmark, but it was pretty early on before we had improved our join ordering algorithms. And even if we run it now, I imagine we're pretty dismal compared to the other databases that are presented in that paper. Or at least no better than them on par, perhaps. I think Postgres, we might do a little bit better. We're certainly not at the level of SQL Server, especially for join ordering. And I think we haven't put a lot of effort into improving our statistics and join ordering, in part because with OLTP queries, we tend to not have a huge number of joins. There's other kind of higher priorities. We definitely want to improve our stats and improve our join ordering capabilities, but for now that hasn't been the highest priority and hasn't been what our customers are screaming most about currently. But yeah, it's definitely a hard problem, and for benchmarks like TPCC, where everything is uniform and kind of behaves nicely, it's easy to estimate the cardinality of joins and things like that. But as soon as you start getting data that's skewed, or start not doing equijoins with primary key, foreign key relationships, then things just really break down. So yeah, good question. Something we hope to improve in the future, but I think it's a problem throughout the database community.
This was great. Sorry for the many interruptions, but this is super interesting. This is why we get so many interruptions.
Awesome. No, that's great.
Thanks.
Questions are good. And actually, is there a hard stop at 8, or I mean, I'm fine to go over a little bit if you guys are.
Yeah, there's no hard stop. I mean, if anyone needs to go, they can go, but we can go over a little bit.
Okay, great. Hopefully I'll get through all the slides, but just in case, I won't be offended if anybody has to drop off before I'm done. Okay, so one thing I didn't talk about was multi-column stats. So this is kind of related to what you were asking about, with skewed correlated data. So this improves statistics for correlated columns. So if you have a predicate like where state equals Illinois and city is Chicago, normally would estimate the selectivity of this by assuming these two columns are completely independent. So we'd estimate the selectivity of Illinois as state equals Illinois as 1/50, and suppose our database has 1,000 cities. The selectivity of city equals Chicago would be 1/1,000. So normally we would just multiply these two together, assuming these predicates are independent, but obviously that is going to be totally wrong. The selectivity will be way too small. And the way we handle that is with multi-column stats. But the problem is that it's difficult to know which sets of columns to collect stats on. There's the power set of different possibilities, true to the n possibilities. So the way we get around this is we use the hint provided by the user of which indexes they've created. So the index is a good hint as to what types of predicates they expect to use in their workload. And we use the prefix. So if there's an index on ABC, in addition to collecting stats on each of the individual columns, we also collect stats on AB and ABC. And the reason this works in CockroachDB is that pretty much all indexes in CockroachDB are ordered indexes. It is possible to create hash indexes, but that's not the default. You would only do that if you had like a workload where you were, had a hotspot because you were ordering by timestamp or something like that. In general, all the indexes in Cockroach are ordered, which means that you can still use the index as long as you have a predicate on the prefix of columns. So currently we only collect distinct values and null counts, but hopefully soon we'll also collect multi-column histograms. All right, so I mentioned that we collect stats offline in the background, but I didn't really tell you how we do this. So we have this command, create statistics, which is similar to analyze in Postgres. And it basically performs a full table scan. So this is what the dis-SQL plan would look like if you had a table that was spread across 5 nodes. So you would need to perform a full table scan, reading the data on each of the nodes. Then we have a sampling phase where we'll sample 10,000 rows for the purpose of creating histograms. And we'll also use a hyperlog sketch to estimate the distinct counts. And then that all gets aggregated on one node before being written out to a system table in the database. And the stats are cached on each node for efficiency. Okay, and then we also collect stats automatically. So you can manually run that create statistics command, or you can just rely on the database to automatically collect stats. So we will run this command automatically whenever a new table is created, when a new column or index is added. So this is relevant in particular for the multi-column stats. Like I was showing, we use the index to figure out which multi-column stats to create. So there's a new index added, we need to collect stats based on that. New column, of course, requires new stats. And then we also want to collect stats whenever a large percentage of the data has changed. So we say about 20%. That's what a lot of other databases use as well. Now, some challenges are, how do we even know when 20% of the data has changed? And we also want to make sure that we minimize performance impact, since we're running this in the background, and this is an OLTP database that's going to be running potentially heavy production OLTP workloads. We want to make sure that if a stats job randomly gets kicked off, it's not going to start hogging all of the resources of the cluster. So this first challenge, maybe seems kind of obvious, that should be easy to figure out when 20% of the rows have changed, but the problem is that with a distributed database, that would require having some kind of central counter that all of the nodes would be communicating with in order to find out when 20% of the rows had changed. And we want to minimize this kind of potential source of contention as much as possible. So what we do instead is we use a statistical approach to collecting stats. So after any mutation, like insert, update, delete, there's a small chance that the stats will get refreshed. And the probability of a refresh is equal to the number of rows updated, inserted, deleted, divided by the number of rows in the table times 0.2. So that's where we get that 20% from. And in addition, in order to kind of have guardrails against any statistical outliers, we will always refresh if there are no stats yet, or if it's been a while since the last refresh. Okay, and the second bullet, minimizing performance impact. So, with the previous explanation of how we collect stats by, having this small probability of a refresh, well, the problem is if these nodes are kind of working independently and they both happen to trigger a refresh at the same time, that could kind of exacerbate any performance issues that might otherwise be caused. So, there's many updates per second, but each stats run can take minutes because it's performing a full table scan if it's a big table. That could take a while. Full table scan can impact performance, but as I mentioned, if we have many stats jobs triggered at once, causing multiple table scans, that could, well, when I originally wrote this slide, this was a while ago. Hopefully it won't bring down the cluster these days, but you never know. It could cause problems. So some solutions that we came up with are, we run the create statistics as a job. So we have a jobs infrastructure that we use for kind of long running operations like import, backup, restore, those kinds of things. And the advantage of that is the infrastructure allows us to, first of all, guarantee that there's only one stats job running at a time across the entire cluster. And if the node managing the stats run dies, another node can adopt the job. So it's resilient to failures in that way. And even with this restriction that we only run one job at a time across the whole cluster, it can still cause too much performance overhead. So we additionally add some throttling to limit the CPU utilization by the stat job. So we do this by kind of, in a very simple way, basically inserting some sleeps as we're reading through the data. Every 1,000 or 10,000 rows, just sleep for a millisecond or two, and that serves to kind of reduce the CPU utilization by the stats job. It's adaptive, so if there is actually a lot of available CPU, then it'll complete more quickly, and otherwise it'll complete more slowly. All right, any questions? Okay.
Just one quick question, maybe just one quick question. So in your cardinality estimates and everything, how do you handle more complex predicates? Like, if you have a like predicate on like the ending of some words or something.
Yeah, good question. So if there's a like predicate on a prefix of a word, then we can treat that as just like a range scan, and we can use our histograms to estimate the cardinality. If we have a like predicate on the suffix or anything in the middle, there's really not much that we can do. We haven't really optimized to handle that case. And I think we basically use the constants that were actually proposed by the original Pat Sullinger paper of, like 1/3 for kind of your standard predicate as a selectivity. So yeah, nothing fancy. Cool. All right, so I mentioned that we in general don't take the data distribution into account, but in very specific cases we do. So of course, latency is important when you're dealing with a cluster that's spanning the globe. And for kind of small tables that are read mostly, we want to make sure that we're not, having kind of large latency hops across the world in order to read that data. So what we recommend that our customers do is actually create multiple copies of those small tables. So for example, if you have like a postal codes table, that's something that you potentially might want to access from everywhere and is not going to be updated very frequently. You would have, the primary index is on the ID, and then you have the postal code. And then we would suggest if you had a 3-region cluster, like in this example, you would create 2 secondary indexes that are actually identical to the primary index because they're keyed on the ID and store the code. And then we allow you to use constraints to pin each of those different copies to different locations. So one would be pinned to US East, one US West, and one in the EU, as in this example. And then the optimizer is at least smart enough in this case to choose whichever index is located in the same geographic location as the place where the query is originating from. So if you run a select start from postal codes in California, it'll use the secondary index that's located in that region. Now, this is obviously not ideal. It's kind of hacky. It's pretty annoying for customers to have to use this duplicated indexes pattern, because what if they added a column but they forget to update all the different indexes? Then they start seeing bad performance. So in the current release, actually, we're doing a huge overhaul of our multi-region support and adding some nice syntax that allows you to just kind of handle all of this under the covers. Basically, we create this concept of a global table, which is what this postal codes table would fall under that category. A table that is read mostly, and you want to have fast read access from all regions. So we are creating this new concept. It'll come out in the next release, which is planned for a couple of months from now. Another thing that we have coming along in kind of this theme of improving our multi-region support is the ability to support geo-partitioned unique indexes. So of course, if you have a geo-partitioned index, and since indexes in CockroachDB are sorted, the first column in the index is going to have to be your partitioning key, say region, for example. But if you have a unique index that you want to be unique on, say, the second column, the index can no longer enforce that. So we're currently working on adding some special checks that actually the optimizer enforces in order to ensure that that second column is unique, or whichever set of columns you've actually declared as unique. As I mentioned, we're going to be trying to move some of that to-SQL planning into the optimizer. So decisions like, do we perform a broadcast join, or do we hash or range partition data before performing the join? Other things like, if you have a key that you know to be unique, again, this example where, with the geo-partition unique indexes, say you want to find the data for customer with ID 5, but you don't actually know which region customer 5 is located in. We're going to first check the local region, because we assume that this workload happens to have data locality with the current region. So if we check the local region, it's probably going to be there. If If it's not, then we can fan out to the other regions. So that'll allow us to improve performance in some cases. And then finally, incorporating latency into the cost model. So making this decision about, do we want to have this two-phase operator where we first check the local region before fanning out to the other regions? That only makes sense if the other regions actually will incur some latency to get to them. If you just have a single region cluster or the other regions are relatively close, then we'd want to just create the fan out query right from the beginning. All right, we are at 8 o'clock, so feel free to drop if you have to go. But otherwise, I thought I would spend the last part of the talk just kind of on theory versus practice. You know, there's a lot of things that I learned in grad school about core optimization, which, you know, mostly turned out to be true, but I think the emphasis has turned out to be a little bit different in practice. So in particular, a lot of core optimization is targeted more for analytics types of workloads where you have these large number of joins. With OLTP workloads, we put a lot of emphasis on minimizing the overhead for simple OLTP queries, like, you know, get me the data for, like I said, customer 5. Just very simple OLTP queries that, you know, we had this heuristic planner before that, although it had problems, it was really fast with these types of simple queries. So when we introduced the cost-based optimizer, we wanted to make sure that we weren't regressing those queries. I didn't quite grasp how important logical properties are for optimization. So these are things like cardinality, which we classify as different from statistics. I don't know if this is how other people describe it, but we have a property called cardinality, which basically is the statically known minimum and maximum number of rows. So if you have a limit 10, we know that there's never going to be more than 10 rows coming out of that relational expression. And that can be useful, like, you know, there's certain types of optimizations you can apply, for example, if you know that there's going to be at most 1 row. Functional dependencies are also super important, like, you know, the key defines the remaining columns in the table. And there's actually a large number of optimizations that we can apply based on functional dependencies. Not null columns are also super important. Columns that we know will never be null, and lots more. So I think I mentioned this before. As of today, there's actually, this is probably a little bit out of date. There's probably a few more normalization rules today, but 242-ish normalization rules, plus or minus, and 29 exploration rules. So this just tells you how important normalization rules are. I think when people think query optimization, they think more like join reordering, you know, index selection. These are all exploration rules, but in fact, especially with an OLTP workload, normalization rules are extremely important. Another thing that's kind of interesting, I'm not sure if other optimizers do this, but in CockroachDB, foreign key checks and cascades are all part of the work that the optimizer does. And these are optimized as post queries. So after the query runs, we perform foreign key checks, which are typically just semi-joins or anti-joins to check that, say, if you're inserting into a child table, that the appropriate value exists in the parent table, and vice versa. If you're deleting from the parent table, you want to make sure that it's not referenced by any data in the child table. And because these are joins, we can actually optimize them just like normal joins. So that's kind of a nice thing about planning these checks within the optimizer. Join ordering. So this is kind of the bread and butter of query optimization, you know, the most important problem, which is true, but you'll be interested to know that we almost shipped version 1 of the CockroachDB optimizer without any join reordering whatsoever. So that kind of tells you for an OLTP optimizer, it's not the most important thing. In the end, we did actually implement a couple of rules. We implemented a rule commute join and associated join, which allowed us to kind of do very basic reorderings, but it was super inefficient. So we actually ensured that if there were more than 4 tables, that we would only reorder the lowest 4 tables in the query tree, because otherwise planning time could just be effectively unbounded. We do have a better join rerouting now. We had a really awesome intern last summer who implemented this DP sub-E algorithm from this paper from Sigmod 2013. I think this is similar to the algorithm used by Hyper. So this is what CockroachDB uses today. And now we order up to 8 tables by default. Again, we kind of limit the number of tables that we're willing to order just in case the time is too great. But if a customer wants to have us reorder a join with 12 tables, this is a setting that they can change. All right, another thing that's important that I think is kind of glossed over in database classes is query cache. This is just an LRU cache keyed on the SQL string. So if a query comes in and it exists in the cache, we can basically skip planning altogether. We just take this optimized memo and build the SQL plan from it. For prepared statements with placeholders, we actually store the normalized memo. So to execute a prepared statement, we will replace the placeholders in the normalized memo and then perform additional normalization and exploration rules. And this is actually something that we want to improve because for super simple queries like, X customer ID equals blah, we shouldn't need to do this additional normalization and exploration. We should just kind of store the default plan. So something, again, on our long list of things to work on. And even with all of the work that we do, oftentimes the optimizer picks the wrong plan. So customers can hint to the optimizer if they want to use a specific index, for example, so they can use the syntax at index name. And they can also hint to use a specific join algorithm. So if you know that you want to use a hash join, you can use this keyword inner hash join, and then the optimizer will choose a hash join. And this also prevents the joins from getting reordered. So if you know the ordering that you want for your joins, you can hint the algorithm like this. And there's other types of hints as well. But this can be useful sometimes. And even with all these tools, we still get customers who are like, why is my query slow? Please help me figure it out. So we have some nice tools that allow us to get all of the info necessary to debug. So this, for example, this tool, explain, analyze, debug, will give us this nice zip file that includes any environment variables that the customer has, all of the stats, the schema, various verbosities of plans. So that basically allows us to completely recreate the environment and debug what's going on. And that is all I had. So as last plug, we're hiring. So feel free to hit me up if you're interested, and happy to take any additional questions.
Thank you very much. And then let's take a few more questions if there are any questions.
I do have a question unrelated to your talk, but you said you're hiring, and some of the students in this group, they're actually looking for internships. Do you also look for interns? Yep,
we're hiring for internships. We have interns all year round. I actually have an intern on the Optimizer team right now. I think some schools like Waterloo, for example, have a co-op program, so we get a lot of people through that. But especially these days with COVID and learning via remote, I think a lot of students are interested in kind of taking some time off and doing internships. So yes, we're hiring for internships and full-time.
And actually, I had one more question. So because you're an OLTP database, do you actually limit the users in kind of how big a query they can write? Because someone could still write an analytical query that would be extremely expensive to run in a distributed system.
Yeah, I think we are still working on admission control and various types of things like that. In terms of limiting the size of an individual query, I think there might be some limits. We don't have any limits at the optimizer level, other than what I mentioned, that if you have a 30-way join, for example, we will only reorder 8 of those tables, and then if you want to set it to 30, you can set that variable, but that's not the default. And I've actually done that for a customer that I think had 18 or 20 something joins, and that was an interesting case because they were actually using our hinting infrastructure to specify the exact order they wanted of those joins. So it was still fast because we didn't do any join reordering, but they wanted to know, is there a better order that we could set? So I basically did that by just, setting our parameter to, allow 30 joins or something, and it still ran pretty quickly. I think just, on the order of several seconds, the planning was done. But I think if a customer wanted to, they could definitely shoot themselves in the foot. And I think there's a lot of security type work that we're doing to kind of improve that and prevent customers from, especially now that we have a Cockroach Cloud, like a hosted service. I think there's a lot of work to prevent certain types of queries from running there. If somebody wants to run this type of query on their own, private deployment of CockroachDB, I think they probably could. They could probably do something, pretty bad to bring the cluster down. But yeah, definitely an area of.
But then it's their cluster.
Sorry.